When discussing stereochemistry as it relates to OChem, it's important to consider isomers. And isomers are two compounds that have the same chemical formula but differ from each other in some respect. Perhaps they have different connections or the spatial arrangement of them is a little bit different. And this is a very busy looking whiteboard here, but it's set up this way because it's a mnemonic device that can help you distinguish between the different types of isomers you might encounter, as well as one way that isomers can be hidden in organic chemistry and MCAT questions. And so the way that this chart is set up is everything to the left of this is something with a different bond-to-bond connectivity. And bond-to-bond connectivity essentially means that if you were to count the exact bonds within a compound, you would end up with the exact same accounting. So you'd have a carbon that was bound to another carbon and perhaps another carbon on this side and two hydrogens. Whereas here, you have a carbon that's actually bound to 4 different carbons. And so you can't count the bonds and come up with the exact same bond-to-bond connectivity, which is very important. And anything to the right of here has the same bond-to-bond connectivity, but it differs in some way, and it is either a non-mirror image diastereomer or it's something that's defined by a chiral carbon. And so we'll go through these one by one and talk about the organization. But the reason that this chart can be useful is because a lot of these names are not very intuitive when you're thinking about them. And this chart is set up in a fairly organized way. You have different connectivity, and then you have the same connectivity, and then these ones over here are defined by chiral carbons. But if you're going through the list, notice that there's a very simple mnemonic device we can use. C, D, E, F, and G. And then you just have to remember epimers, anomers, and meso compounds as distinct variations of these. But C, D, E, F, G will help you remember the names and how these different types of isomers are described. And so we'll start it out with constitutional or structural isomers. And these are things that have a different bond-to-bond connectivity. And so there is a different accounting. For example, in this one, we have carbons that are only attached to either 2 carbons or 1 other carbon. Whereas in this example, here's a carbon with 3 attachments. Over here, here's a carbon with 4. And so the bond-to-bond connectivity is a little bit different. Constitutional and structural isomers will still have the exact same chemical formula. In this case, it's C5H12. In this case, it's something with a few bromines. But notice how these are still going to have the same overall chemical formula. This one has 2 bromines and a hydrocarbon backbone. But notice that there are differences. Here we have a carbon that's attached to bromine, 2 bromines. Here we have 2 adjacent carbons that are attached to their bromines. And here we have 2 carbons that are not adjacent that are attached to bromines. And so this is a different type of connectivity. And something about constitutional or structural isomers is that they have very different chemical and physical properties because they are very much different compounds that just happen to share the same chemical formula but nothing else in common. So when you're dealing with constitutional or structural isomers, these are the ones that are the most different, and they have very different chemical and physical properties. So be aware of the fact that they're constitutional and structural. They can be described as both. And yes, they are isomers because they have the same chemical formula. But other than that, they are very, very different compounds. Now we'll move on to ones that have the same bond-to-bond connectivity, and we'll go through them one by one. First, we deal with diastereomers, which are isomers that are not mirror images of each other, but they do have the same connectivity. However, they have different chemical properties, and this is because of structural differences that are fairly pronounced. Within diastereomers, we have 2 different subtypes. We have geometric isomers, and geometric isomers are defined by the fact that if you have a cyclic compound or if you have a pi bond, you don't get free rotation about that bond. And so that means that you can have one substituent that goes up and the other substituent that goes down, and that will not change. And so the hindered rotation around a cyclic or pi bond is what makes a geometric isomer what it is. Of geometric isomers, there are 2 types that you may have already encountered. There are cis-trans geometric isomers and EZ geometric isomers. Cis-trans is something you use if there are only two substituents that are not hydrogen. And in this case, cis just means that both of them are coming out on the same end of that double bond, or if it's a cyclic compound like this, they're both coming out up from that hindered rotation there. So cis and trans essentially means that if it's cis, then both of the substituents, the unique substituents, are moving in the same direction, whereas trans means that they're on opposite sides of that double bond. So one goes up from the double bond and the other goes down, and we would draw in two hydrogens here, and you'd notice the hydrogens alternate in this way as well. So cis in the same direction, trans in opposite directions relative to that double bond and the spatial orientation there. Now, E and Z are very similar to cis and trans. The only difference is that you use E and Z when you have more than two substituents that are not hydrogen and that are unique in some way. And when you have something like this, you consider which ones are the highest priority substituents, or a lot of times with hydrocarbons, it's not about the priority as much as it is about how hindered are these different substituents. But essentially, if you have several unique substituents more than two, then you consider the biggest or most significant ones here. And so here we have this substituent there, which is, very hindered, and it's a tert butyl group. And then here we obviously have only the methyl group there that we consider. And so what you'll notice is that when it's E, that means that they're on opposite sides of that double bond. The big one over here goes up in that direction, and the most important one on this side of the double bond goes in the down direction. So that is E. The reason it's called E goes back to the German word root, but the best way to remember E versus Z is a simple mnemonic: Z equals same side. And so the Z ones are going to be on the same side. So with relation to this double bond, on the left side here we have the tert butyl group, which is very significant. On the right side, obviously the methyl group is going to be the one that is the higher priority, more important substituent. And so because they're both on the same side, they're both on the top side of this double bond, then this is a Z conformation because they're on the same side of that double bond, whereas here the big one is over here and the big one is down here. And so if they're on opposite sides relative to that double bond, then it becomes an E geometric isomer. So cis and trans you use when there are two important substituents. E and Z you use when there are more than two, and you have to decide which ones are the highest priority, and then you look at the orientation of those high priority ones relative to the double bond or relative to a cyclic compound which has hindered rotation about that bond, so that when something's stuck on one side or the other, it's not going to rotate freely as it would with other types of compounds which can rotate about single bonds. So those are two geometric isomers, cis and trans, and E and Z, and those are one of the subtypes of diastereomers. The other classification or subtype of diastereomer is the epimer. And an epimer is something that is the same at every chiral carbon except for one. It only differs at one carbon. And so the epimer is something that differs at only one chiral carbon, whereas an anomer is a subtype of epimer that involves a ring closure at the epimeric carbon or the epimeric atom, but usually it will be with regards to carbon. An anomer is something that you will be responsible for because it's highly important in ringed sugars like glucose. Glucose has an alpha form where the OH group looks like it's going down, and a beta form where the OH group looks like it's going up relative to the additional leg that has the carbon in the OH group. So if it's beta, the OH group goes up and the carbon and OH group also go in the up direction. Alpha, it goes opposite to the downside. But essentially alpha and beta are ways of describing anomers, which are chiral compounds and isomers that differ with one chiral carbon, and it happens to be the chiral carbon where the ring closure is occurring. And so with sugars, you'll be dealing with alpha and beta sugars, and that is purely due to the chirality of that anomeric carbon. And notice that Epimers and anomers are the first ones in the column where we're looking at things that are defined by their chiral carbon. So these are diastereomers that are not mirror images of each other because they don't differ at every chiral carbon, but instead they only differ at one chiral carbon, so you can't have a perfect mirror image. But they are defined by that chiral carbon, and so they now move to this right side of the chart. And then we get into perhaps the most significant type of isomer that you'll encounter, and these are enantiomers. Enantiomers are the mirror images, and one mnemonic device people use to remember that is they think of an ant in a mirror, enantiomer, and that's the enantiomer, which is the mirror image. And so if you struggle with that name, think mirror and mirror image. It's a mnemonic that works. And these are something that have the opposite absolute configuration at every single chiral carbon. And so every single chiral carbon there is going to be different. If there are 3 chiral carbons and one is SSR, the other will be RRS. And so an enantiomer has to be a perfect mirror image of its counterpart, which is the other enantiomer. And these are compounds that you often see in discussions of optical activity because they differ to each other only with regard to their chiral properties. And remember, the 2 chiral properties where chiral compounds differ from each other are in how they rotate plane polarized light and how they interact with other chiral compounds. And so enantiomers are often useful when you're considering optical activity or perhaps enzyme activity that's based on the stereochemistry of these pieces. Here we have an enantiomer, and this is structure. And if you go through the structural diagram here, we'll prioritize this one, the COOH, as number 1. Or sorry, we'll prescribe the OH as number 1, the COOH as number 2, and the methyl group as number 3. And here the OH will be priority number 1, the carboxylic acid group is priority number 2, and then here the methyl group is priority number 3. Remember that priorities are defined by the highest atomic number or highest molecular size, and then if there's a tie, for example, with these 2 carbons, then you move to the next one. Now, because this H is the lowest ranked one and it's moving away from us, we can just draw the connections directly. And so we see this movement, this is going in a counterclockwise direction. So that will be the S form. S is for counterclockwise. And here, if we draw from 1 to 2 to 3, then this will be in a clockwise direction, and that is the R group. And so enantiomers are something where this one is fairly simple because it only has the 1 chiral carbon. But if they're larger compounds with multiple chiral carbons, they have to differ in their chirality at every single one of those in order to be enantiomers. And once you're dealing with enantiomers, then you start to deal with things like plane polarized light and looking at the optical activity of these compounds. So these are definitely things that are defined by the chirality of their carbons. And so that's when you're looking at enantiomers there. You're looking at something where chiral carbons are the only differences, but the bond-to-bond connectivity is the same, and they can be mirror images of their counterparts. We'll move down to meso compounds before we get to Fischer projections. And a meso compound is a very interesting thing because it is its own enantiomer. It's a compound that is a mirror image of itself. And the reason we can say that is because there's an internal plane of symmetry. So here we'll look at the cis-1,3-dichlorocyclopentane. That's a long name, but essentially it's a cyclopentane with chlorines that are cis because they're both going up. And they're in the 1 and 3 positions here, or 1 and 3, whichever way you want to number it. Notice in red here, we've drawn an internal plane of symmetry. And if we were to go and account for the different carbons here, what we would see is that this and this were both chiral carbons. One of these would be R and one of these would be S. But rather than going through and analyzing the stereochemistry and the absolute configuration at every carbon, it's a lot better to look at, is there an internal plane of symmetry? And if there is, then you're dealing with a meso compound, as long as this compound has some chiral carbons. If it has chiral carbons and an internal plane of symmetry, then that's a meso compound. We also have one down here, and again, we can draw this internal plane of symmetry, and it just so happens that the methyl group is facing us in both cases, and the OH is moving away from us. And so these are identical carbons with, in terms of their connectivity, the only difference is their stereochemistry, their absolute configuration. And so meso compounds are interesting ones because they do have chiral atoms. And when you see chiral atoms, your inclination is to think that there's optical activity because chiral carbons and chiral atoms in general have optical activity because they rotate light. But because this one has chiral carbons that are of the opposite absolute configuration, one of those carbons will rotate light in one way and one will rotate it in the opposite direction. So it's equal parts D and L in terms of its rotation of light. So this is actually an optically inactive compound, even though it does have chiral activity. So be aware of meso compounds because a lot of times the inclination is to look at something, find a chiral carbon, and assume that therefore it must rotate light. But there will be no net rotation of light because this meso compound is one that has counterparts where one side will rotate it in one direction and one will rotate it in the other direction. And then the last thing we come to is not technically a classification of isomer as much as it is a way of displaying or describing a type of molecule. And this is the Fischer projection. And here's a fairly simplified one, but remember with Fischer projections, they have vertical lines and horizontal lines that mean different things. The traditional way that people often describe the Fischer projections is that the vertical is going into the page and the horizontal is going out of the page, or vice versa. But I think the better way to look at it is that the vertical lines are the carbon spine. A lot of times when you're dealing with a complex carbon-containing structure, some carbons are going up, some carbons are going down like that, and others are shooting off one way or the other. The best way to think of it is that the vertical lines are the carbon spine, and the horizontal lines are the protrusions, the substituents that come out of the carbon spine and move outwards sort of horizontally relative to that. So the vertical ones, and especially with a large Fischer form, you can look at the vertical lines as the carbon backbone or the carbon skeleton, and the horizontal lines as the offshoot. The reason that this is important for a discussion of isomers is because this is just one depiction, but remember whenever you have a single bond, things can rotate about a single bond, and so it can often be used to disguise compounds that may or may not be enantiomers. And so let's look here, let's move all of these one position. We'll rotate these all 90 degrees. And what happens is when we do that, we actually end up with this exact compound here. And so these are not enantiomers of each other, these are the exact same compound. It just happens that we've rotated about a single bond in a way that makes the Fischer projection look different. Now in this case, there's no way we can rotate these CHO groups and the OH groups. There's no way you can do this, and you can do this at home if you'd like. There's no way we can rotate this either clockwise or counterclockwise where this becomes superimposable to either of these forms. And because of that, since we cannot superimpose them by rotating about this, then therefore this is going to be an enantiomer of this form because there's no way to superimpose it, but the connectivity is the same. Another thing that's useful to consider when you're dealing with Fischer projections, and this is why it's such an important part of isomers, is that a lot of times it can be used to disguise a meso compound. And so let's look at, we'll just draw a meso compound here like this, and let's say Cl here, Br here, and H there. Now this is a meso compound quite clearly. We can kind of see that it looks like a mirror image of itself relative to this Fischer form. However, one thing that's very tricky is we could also rotate all three of these substituents. So we have Br here, Cl here, and H. What we've essentially done is we've taken them all and rotated them one position. We move that one here, we move that one here, and we move this one here. And what's interesting about this is that this is still the same compound. All we've done is just swiveled around that sigma bond here before the last carbon. And so a lot of times you can see meso compounds, which are their own enantiomers, disguised in Fischer forms because they're not neatly laid out where the Br is here and there, and the H is here and over there. If it's laid out like that, it's fairly easy to see it's a meso compound. But if they ask you a complicated question looking at something like this, and they say, is this optically active? The first thing you can do is look at it and say, okay, well, clearly there are 4 different substituents, so therefore it has chiral carbons. But notice that we can find ways to rotate this terminal carbon, rotate around that sigma bond to now where it's still a meso compound, but it's obscured because it's not obvious that this Br actually can go over there and that this chlorine group can go up to the top. And so be aware of how Fischer forms can be used to obscure different things. It could be superimposable because you can rotate it one way or the other, and so you can have enantiomers or identical compounds depending on whether you can rotate it and perfectly superimpose it or not with the Fischer form. And you can also find meso compounds being disguised by Fischer projections just because you can rotate things around that sigma bond, and this terminal component can see rotation in many directions. So this is probably the most complicated and tricky questions that you'll encounter will involve those Fischer projections, because Fischer projections don't account for the swiveling or rotation around sigma bonds that a lot of compounds are very capable of. But that is a very, very nuanced point that is a very high-level thing that you could be tested on. In general, if you can understand isomers and the different types, then you're going to be able to answer a lot of questions fairly straightforwardly. And I think the best way to do it is by using this chart and its organization so that you can remember what a diastereomer means, what an enantiomer means, and so on. So remember that on the left side, we're classifying these by whether they have different bond-to-bond connectivity, or, as we move to the right, if they have the same bond-to-bond connectivity. And then after that, we look at, are they defined by a chiral carbon? If so, we're looking at enantiomers, perhaps Fischer projections that obscure them, or something like a meso compound where the chiral carbons creating a mirror image are the major factor that we consider. And once you understand that, then I think it's going to be easy to reproduce this chart. Just going C for constitutional, D for diastereomer, E for enantiomer. Remember, an ant in a mirror is a way that they use that. So you can remember enantiomers are mirror images. Then you get to F for the Fischer projection, a common tripping point when you're trying to classify different types of isomers. And then geometric isomers, which are created by the hindered rotation around those double bonds or the cyclic bonds, ones that can't rotate freely and pivot around that sigma bond. And then once you get the C, D, E, F, and G, then all that's left is epimers, anomers, which are both things that differ at one chiral carbon, the anomers being the ones where the ring closure occurs at that chiral carbon. And finally, meso compounds, which can be very misleading because the meso compound has an internal plane of symmetry, so it has chiral carbons, but they cancel each other out. And so as a result, you end up with no net optical activity despite having a compound with chiral carbons. And hopefully this was a very effective way of laying out all of these pieces so that now you can distinguish different types of isomers from each other and stay clear on the definitions of these different types when you encounter them in one of your problems.